Good morning, everyone. I am Katie at the Lighting Design Lab, and it is almost 10 o'clock, but we're going to start here. Let everybody trickle in, get their coffee. It is May 30th. It's my sister's birthday, so happy birthday to my sister, who is definitely not on the call. She works for the stranger. She's not interested in codes. You have made it to the third of our 5 courses that Duane is, we are grateful to for Duane doing these. And today he's got Shawn as a guest. And we've got a lot of water heating stuff to go over.
All right. You tell me when you want to move slides there, Katie, if you want to give them another minute to get settled.
Yeah, it's 10 o'clock straight up, so let's leave this up for another 10 seconds or so. People are not so slowly trickling in, coming in droves.
We're watching the auditorium fill up right now.
That's right. Keep the noise down. Find your seats quickly. All right, let's go to the next slide now, Duane.
Oops.
Okay, just a few things before we begin. If you haven't taken a course through the Lighting Design Lab, all the attendees are on mute, but there is a way for you to ask questions, and we encourage questions. And there's a little chat feature in GoToWebinar. Depending on whether you're using it, whatever version, you'll have to find where it's at. And you can ask any question there at any time, and we will get that addressed as soon as we can. We are recording this, and it will be available on the Lighting Design Lab's website within the next week or so. And our email address is right there on the screen if you have any comments or questions during or after the webinar, anytime. You can go to the next one.
Yeah, and by the way, do ask questions. There's a very strong likelihood that if you don't know what one acronym means, that there's 20 or 30 other people that have the same question.
That's true. There are nearly 150 people signed up, so you are not alone if you are questioning something, I am positive. Lighting Design Lab is a part of Seattle City Light. We're Seattle City Light employees, and we thank our sister department of construction inspections, where Duane is at, for partnering with us, and Shawn from Ecotope today to give you more practical applications of what Duane's going to talk about.
Alrighty then, and if in case the automatic thing didn't tell you, you're being recorded, or everything is being recorded here.
Yep, even the chat.
So those of you who are veterans of these webinars for the last couple code cycles recognize this slide. Just to say that unlike the rest of the country that's arguing about whether to go forward or not, we are legislatively obligated to move forward, and we are trying to figure out the most sensible and economical way to do it. And likewise with this slide, of our 4 big principles for how we move the Seattle Energy Code forward, we'll be dealing with the no internal combustion buildings thing, that we're moving away from fossil fuel combustion, because we can't be building stuff that burns gas through the 2020s and expect to be carbon neutral in the 2040s. And meanwhile, we also can't just waste that limited amount of clean electricity we have on electric resistance, because we got to use a lot of our clean electricity that's available now for converting the entire vehicle fleet and all the existing buildings over to electricity. So we've got to use our clean electricity efficiently. That bottom line there is the bottom line, that the buildings we're building now have to meet that carbon neutral 2050 target without any major surgery. Shawn, tell them who you are.
Great, thanks, Duane. Name is Shawn Oram. I am a principal mechanical at Ecotope. I've been with Ecotope for 22 years. I've been working on heat pump water heating, research and design for about 12.
And apparently you think it's a good thing, huh?
Yes, it works.
Okay, he's a man of few words. And just to accentuate what we discussed a minute ago, we're moving on that diagram on the left. We're trying to follow that triangle of reddish area there on the chart down to something close to zero in the next couple of decades. And we did find a couple years ago with our ongoing surveys of fossil fuel use that it was going up in buildings, and that's where we came with these rules for heat pump space heating and heat pump water heating. With the diagram on the right, which is the state trajectory towards a 70% reduction in new building energy use, you can see that we are pretty much on track, and yet the remaining distance to the 70% reduction means that we have to somehow, the darker green lines are commercial buildings, somehow get another 40 or so percent of existing energy use for new buildings squeezed out of that system. So we've got a little ways to go. And this is my non-engineer's diagram that I made while trying to figure out how this works. But basically, we'll be talking about heat pumps a lot in this next hour and a half. And it depends on this sort of magical fluid that has a boiling point that is just exactly in the right spot, so that that cold liquid you see that's circling around at the bottom left there goes into the evaporator. It's gonna actually be cold enough that it's gonna pull heat out of that cold air, so that the air going out the other side of it is even colder, and what comes out is a warm gas instead of a cold liquid. And then the compressor is going to squeeze it really hard to make a hot gas out of it, and that gas over on the right side gets transferred into that cold water, making the cold water hot water. It seems magical, and it kind of is, and it's running at what is it, Shawn, about 35% as much energy as is required to do the same work with electric resistance.
Yeah, that's about right.
And this was in the current code cycle, which is drawing to a close. This was just a Seattle thing for water heating, and now it's been picked up by the state, and we're moving forward. So mostly the state picked up the Seattle rules with some modifications that actually, in many ways, made it better. But especially for new construction, it's very similar to what you see already in Seattle. And in the state code, though, one big difference is that it says that for supplemental heating, which there are rules we'll go through, you can use gas or electric resistance for that. And for Seattle, supplemental heating allows some electric resistance, but not gas. And we have lots of exceptions in there. The ones in bold, by the way, at the bottom are Seattle amendments, and the one at the very top is something that allows minor amounts of electric resistance water heating around a building, especially like an office building might have very little overall. The one I have in red mentions this NEA commercial advanced water heating spec, and that one is a recent addition to what's already been in use for a while for residential unitary water heaters. But in this case, they're looking at a whole system, and they're checking the performance and the satisfaction from getting the hot water when you need it, how it all works. And in this code, if you're taking that alternative, you can pick any of their tiers of efficiency. I say on this slide, we're going to mention the qualified products list, but that'll be a few slides down as we go through this. But now let's turn it over to an actual engineer to explain you in more engineering terms what's going on here.
Thanks, Duane. Okay, so we're talking about heat pump water heaters, mostly central heat pump water heaters. And before we start, we'll just kind of review the basic 4 pieces inside of a central heat pump water heating plant. So along the bottom are kind of these pointed out. So we've got a heat pump, and that's over to the left. Their job is to primarily make hot water inside the primary hot water storage tank. So that would be the second component. So you've got the heat pumps on the side, you've got the primary hot water storage. It's shown as a single tank there. It can be multiple, series or parallel. So both of those piping arrangements will work. We've got temperature maintenance system. This is just trying to keep the line in throughout this large building primed and hot, ready to go, so that when apartments or units pull water off of it, it's right there kind of sitting, right outside the unit and not all the way back at the plant. So we absolutely need that. The final piece is the mixing valve. The mixing valve is super important here. There's some variability in the temperature on those supply sides, and so having mixing valves that can respond are really important for central heat pump water heating systems. And I guess we'll continue here. So there's a swath of products sort of out there. You may recognize some of these, but as Duane mentioned, this is the heat pump water heater, and these are sort of the engines. These are designed to be much smaller than sort of an equivalent gas load, and the idea is to couple these smaller machines with a bigger vat of storage. So hot water is sort of a big dump load, and you're trying to sort of trickle in and heat up a big vat of storage, and that's the strategy with efficient central heat pump water heating.
It's not a boiler, huh?
And it's not a boiler. It does make hot water. Duane covered a bit on how they work. The diagram that Duane showed, this is sort of another translation of it. The one on the bottom kind of shows that there's an outdoor coil, and the indoor coil is actually the tank of water. And so that is kind of the primary loop that Duane showed earlier. And then for the engineers out there, there's what we call a pressure enthalpy curve. And this is sort of a diagrammatic, using a pressure enthalpy curve. It's a function of the refrigerant. And so you start to look at the properties that you need to sort of perform the work that you're asking of it. I won't get into how that diagram works, but it's a really important diagram. Next.
Only for people who are professionally qualified, huh?
Yes.
Oh, wait, it actually did make a little change. Anyway, go ahead.
Okay. So getting back to there's 2 types of heating cycles. One is a single pass. That's what's shown on the left. This is very similar to, the single pass, the one on the left, is sort of how most of the newer heat pump water heating gear are set up. The idea there is you're heating the water in a single pass through your machine up to your desired temperature. The flow rates are much slower in these single passes, and so you can't actually do real-time instantaneous water heating. You need it to be coupled with storage. That's the only way this sort of works. And you get the benefit of a much smaller machine, so the connected load is much smaller. On the right side is what we call multi-pass. This is very similar to how gas boilers traditionally are set up. There's 10 degrees on each pass, and you sort of start at the bottom and you work your way all the way up until that tank is satisfied. Most of the CO2 stuff, or most of the heat pump water heaters out there that are performing well, are kind of sticking more to the single pass arrangement. That said, we've seen some multi-pass systems out there that are also delivering pretty good performance. So I think both of them are viable, and they certainly are within the context of this code. We mentioned the primary storage tanks. We like to think of these as battery banks. And you can see there's an example installation. This is a large project, somewhere around 240 units. And we can see there's about 4 or 5 500-gallon storage tanks. So this is a large installation of storage. This building is also load shift capable, which we may talk about later, but that's sort of a future component. But the key here is that this is a big battery bank, and the hot water loads in our buildings tend to be, based on occupancy, but there's usually sort of peaks in the morning and the evening, and you're buffering up all of that storage to handle those big draws. And by doing this with a lot of storage and a little engine that could, we essentially we get the benefit on the grid side, and we don't typically run out of water when we've got this big big storage vat stored up.
So ideally, how many hours a day would a heat pump run to keep all that hot for the to have it ready for that morning rush?
Yeah, that's a good question. What we've sort of settled on is about 16 hours, and there's a program that we've developed called Ecosizer. Some folks have used it, some haven't, but it's a really good tool for sizing these systems. But that tool is centered or based around a 16-hour runtime, and what that does is gives you sort of 8 hours of float to kind of make it up. The other thing that it does is that it'll facilitate load shift, and so there's a couple of peak times in the grid where the utilities would love for us to not run these heat pump water heaters. And there's sort of teases about this load management in the new code, but that's really, kind of a big picture. That's what's happening here is we're really trying to, set these systems up so that we can actually have a flexible, kind of grid operation. And so we've got a little bit of flexibility, but the 16 hours gives you 8 to sort of buffer up.
Okay, and we will get to an Ecosizer slide in a little while.
Okay, so moving on, that third component is called temperature maintenance. This is just maintaining the temperature inside of the loop. And one thing to keep in mind is traditionally we used to send the temperature maintenance return into the primary storage, and we had gas or electric boilers to kind of just to heat it all up all together, one load. And one thing that happens when you do that with a heat pump water heater, it doesn't end up working very well, especially the single pass machines. And so what's been developed is sort of an approach really around temperature maintenance reheating. And there's 2 strategies. You either have a dedicated heat pump for that temperature maintenance load, or you use a concept called a swing tank, and we'll get into that. But the idea here is that the hot water return comes through this swing tank or temperature maintenance tank, and that load is sort of dealt with differently than the primary, cold to hot water load. That's, the primary water you're using. So that's one of the key pieces to maintaining efficiency in a system is if you decouple these 2 loads, they're much different profiles, 110 to 120 on the temperature maintenance. And on the cold water side, we want to take 50-degree water and make 120 out of it, or even in some cases 150. So this system is really important. You cannot do a big building without a temperature maintenance system. And key to this is, trying to get a hold of those losses, because they're all losses that go into a building, temperature maintenance. It's the penalty you pay to have the water close to your unit.
Yeah, and in fact, if it's cooling season, those losses are actually building up your cooling load as well.
Yep, overheated, double loaded corridors. So I mentioned the kind of the single pass and the multi-pass. So this is an example of 2 variations of single pass. And single pass machines, remember, will heat the water up in 1 pass through the machine. So usually 50 to 150 or 140, depending on what your set point is. But really the focus here, so there's 2 single pass setups here, which is 50-degree to 120. But the difference on both of these systems, there's sort of a swing tank, which I mentioned before, and then there's a parallel multi-pass system. The swing tank works by bringing that 110-degree hot water return on that left-hand side diagram, bringing it into the bottom of that swing tank, and then the coincident hot water flows in the building will end up mixing with that return, and so it'll end up doing the heating for that return without actually touching the heat pump. And by doing this, you can maintain your COP of your system. But once that return goes back into that primary storage, the COP just severely drops. And then the scenario on the right is called parallel multipass. And this is what you want to do when you've got a very large hot water circulation load, where the swing tank just might get overwhelmed. And so usually bigger buildings will adopt this parallel multipass system. We've done both. They both work, about the same efficiency, plus or minus, depending on that secondary heat pump. But these are two strategies that will work. Most of the reps are pretty dialed into most of these strategies, so that's going to be super helpful for the design community trying to address these requirements of code.
And Shawn, you mentioned COP, so maybe two questions. What's the best COP for a large building you've been able to come up with, and what's typical?
Yeah, that's a good question. So first, COP is a term called coefficient of performance. COP of 1 is resistance. So you put 1 unit in, you get 1 unit out. The magic of heat pumps are you put 1 unit of energy into that compressor, you get between 2 and say 4 out. And one thing that's really important on this COP is that the region is sort of grabbing onto what's called a system COP versus a single piece of equipment COP. And so most of the equipment is rated at an individual equipment COP run through a lab through special conditions. But what NIA and kind of the region hot water, advanced water heating group, what they're trying to do is essentially develop what's called a system COP. And so that takes into account all of the temperature maintenance. It takes into account your primary heat pump. But to get to the answer to the question, so the range that we've seen in big buildings between 1.5 to 2.5, and that would be taking the hit for temperature maintenance. So 1.5 to 2.5 would be all in. If you've got a heat pump in a parking garage or you're using a CO2 based heat pump product, getting a COP of 2.5 is pretty straightforward. When you start taking heat pumps that aren't optimally designed for our outdoor weather, those tend to lose a lot more capacity, and so that will really drive your COP down, as another strategy. And so when you've got pieces of equipment that struggle below 40, recommendation is to put them in a below grade parking garage. Those garages rarely drop below 40. So long answer, but basically 1.5 to probably 2.5, 2 3/4, about that range is sort of the best we've seen out there.
Thanks.
Yep. Okay, and then the final piece is called the thermostatic mixing valve. This is a device, super important. It's required for code for anti-scald protection. It's definitely recommended to get a good, reliable mixing valve because the temperatures that we're usually making are above kind of the safety temps, usually 140, 150. Sometimes we're making 170 with our heat pumps, depending on what the agenda is. So it's super important to have a thermostatic mixing valve, and more importantly, one that is actually digital or modulating, one that can actually respond. The swing tank, the reason it's called a swing tank is because the temperature swings up and down, as you can imagine, based on when the flow happens. So there is quite a bit of variability in that swing tank, but if you're using a properly sized and selected thermostatic mixing valve that's motorized and kind of can respond quickly to changes, those usually do a pretty good job at maintaining supply water temps.
So just a little code insert here. if you got a simple building with a single riser, single zone, then the pump is just turning on and off based on a 10-degree reduction in the supply water temperature. There's if you could do it that way, or you can have an automatic time switch that just turns the pump off during some scheduled unoccupied hours and requires a manual switch for extended, like, 3-day weekends and stuff if you don't need hot water in your building. Multiple risers, it's a little more demanding, that the pump turns off during extended periods. I think we've refined extended periods to mean 4 hours in the next code. Then you've got this balancing, which Shawn was just talking about, and in Seattle you've got to have this self-actuating thermostatic balancing valve for one of these systems, and I believe that is so that if there's one of the risers that's drawing a lot, everybody got up early that day, that's getting the right heat without circulating it through everybody else's risers. Did I get that right, Shawn?
Yeah, that sounds about right. Yeah, the thermostatic balancing valves go on the top or bottom of the risers, and they help to regulate the flow through them. One thing I will just add to that point, in a multifamily building, we've seen demand pretty much around the clock. It doesn't matter what type, we'll see some sort of demand. And so you have to be really careful. Turning a pump off in a big building is a little bit scary. And so you have to make sure that you don't need the water. But typically with our multifamily projects, we're seeing demand throughout the 24-hour.
And I believe that in the new code, it exempts residential occupancy and institutional occupancy buildings from any requirement to turn the pump off, just for that reason.
Right. All right. So we've got these key design considerations.
All right. You're going to learn all about them, but first you've got some examples you want to tell us about.
Okay. Here's a recent example. This was in Pasadena, California. This was completed last year. It's a 77-unit senior housing project. This was actually a retrofit of a round 1 heat pump water heater that was installed kind of in some early programs, and that one didn't end up working very well. And it was all the sort of early failures that you'd expect when not knowing much about heat pump water heating. But so we came in after and sort of put this system in. This is a six Senko 2 based system. There's large storage. This is Pasadena, so it doesn't freeze down there. Most of the plants are typically on the roof in California, but this is a pretty nice install down there. And once we got this sort of up to installed, we had really good consistent hot water.
And those 6 units, those 6 Senko units you're talking about are on the left side there, and
Correct.
Those are like the size of a big suitcase. Is that right?
Yeah, they're 2.5 by 2.5 by 2 feet, little condenser units like we see on a lot of projects, and they're rated at about 15,000 BTUs per hour, so they're small. But this is a nice option because it gives you quite a bit of redundancy, reliability there. So if one of those were to go down, you'd still have 5 others. So that's a really important consideration, is reliability, redundancy in your designs.
And with that configuration, each one of those can serve a dozen units or something like that.
That's about right. Yep.
Okay, the next one.
Okay, this is another project. This is quite a bit bigger project. This is 525 units. This plant was divided into 2 pieces. So there's kind of 2 parts to this building. This is a project in Seattle area. This is set up as a primary heat pump and a swing tank and this one's also load shift capable. And so this one's able to switch out from 4 to 9 p.m. as well. But this just kind of shows you the size, when you get into a bigger project. This is a 360 unit plant. So there are two 30-ton heat pumps on the left and about 2,000 gallons of storage on the right. Piping's all sitting in the ceiling. One thing to note is those heat pumps, this whole plant is inside of a mechanical room, and the heat pumps are ducted out, and there's a sort of purposeful grill, makeup air grill coming into the room. And so that's one thing to remember, is that the heat pumps need access to a lot of open air, a large cavernous below grade garage or outside. You cannot place these inside of a closed room.
We lost you for a minute there.
Okay, sorry.
You were talking about needing big amounts of air to blow through the room down there.
Yeah, so you can't really see what's going on here, but the heat pumps are exhausting quite a bit of air out of the room, so they're ducted out, and then there's a makeup air grill coming into the room to kind of make that air up. But this is open to a 2-level below grade parking garage, so there's a lot of air in there and a lot of heat with all the ground contact.
Are those tanks 500 gallon or 1,000 gallon each, or what?
They're 500 each. They're insulated. They're sitting on an R10 pad, and then they're also wrapped with an R11 jacket around them. So it's about an R25 tank wall, which has very little heat loss.
So that's something like 3,000 pounds, right? That's a lot.
Yeah, that's a lot. Yep.
Okay.
So now might be a good time to ask this question from Steve Chan, and maybe you guys get into this later, but he's wondering then how much more room do we need to request from architects compared to a boiler system? These are big systems.
Yeah, that's a good question. I would say that compared to, like, when we've seen architectural plans, when we're addressing design, a traditional boiler room is actually, I would say 1.5 times, and the caveat being that we put the heat pumps outside of the boiler room. And so what I would say is a strategy to consider is that in a below grade parking garage is that you start to pipe them with one wall completely open, and so there's some strategies about that, but basically the room that it's in, I would say is like 150% larger than your traditional boiler room. But then you've got to also have some space outside of that room for the actual heat pump gear. So when you factor that in, it might be a 2x space.
Thank you on behalf of Steve.
Okay.
And if you're using a CO2 based system, then it can go in the room.
Most of the two products that are sort of currently available now will both operate well below Seattle and even Spokane design temps. Third project, this is a project called Baby Authority. This is an 11-story high-rise 80-unit senior housing project. It was one of the many sort of public housing projects that were heated with electric resistance. And so this one was just a basic replace the electric plant with a heat pump water heater. This one in particular was built in a factory, and so this is sort of chasing the regional goal of developing plug and play heat pump water heating skids. With what's sort of out there in terms of our existing building stock, there's a lot of focus now on scaling this sort of transformation. And so this is one approach that essentially was built off site. It was tested. Everything was set up in a factory. It's dropped in. A day later, the thing's online and operating. truck it up, crane it up, and install it. So this is pretty nice because you're not going to have any issues. You drop it in and it's ready to go. And so there's a lot to be said about this if you're trying to do mass transformation of gas to heat pumps.
Can I ask you then, Shawn,
Yeah.
about whether there are any issues with unions and how it works out with inspectors if you're building something off-site and just craning it in like that?
Yeah, that's a great question. I think it's, I don't know if they've actually gotten into that level yet, getting into kind of the, where the jobs are happening. So I think that's, to be determined, but I think that, in terms of the plug and play and what the potential is, for this, I think there's positives on both approaches. But yeah, that's a good question. And, this is certainly one of many ways to deliver. And so if there's issues, then these can obviously be built on site as well.
Yeah, so I guess the words to the wise would be talk to your plumbing inspector and electrical inspector first, so they're not being blindsided by this, and they might want to come to the factory, they might want to have you leave certain things unfinished inside of that enclosure or something like that.
Right.
I mentioned that there's a qualified products list in that NIA advanced water heating spec. There are, on the residential side, for the little unitary things, there are dozens or hundreds of them, but I think there are 4 systems that are on their list, or there was last time I looked at it. So these are for the whole system that is being evaluated at one time according to their criteria. So at least you have some assurance that a certain configuration of different specific components will meet their criteria. The permits for heat pump water heaters are a little complicated. They were complicated before, but now they're more so. So just be aware that on the mechanical side, on the left there, in my department, they'll want to, for plan review and for inspections, they'll want to look at the heat pump water heater itself. And then, Shawn mentioned that massive amount of air that's got to move through if it's an interior space. So where those fans and ducts are that are making that happen, they'll want to look at where it is located on the rooftop or elsewhere on the site to make sure that you're within the land use and zoning height restrictions. Look at your refrigerant piping. Noise is an issue that you have to take very seriously if you're near a property line. Structural. On the far right is a boiler, and these are not boilers that heat pumps are, but any storage tank with hot water in it that's more than 120 gallons has to get looked at by a boiler. And for reasons that go back in foggy history, every one of those tanks has to have its own permit. I think that they want to mostly look at your seismic bracing and insulation and structural support. You can imagine that 500 gallons of really hot water could be quite a hazard. When those are all in ducts are kind of in a row, then the county plumbing inspectors will look at all the piping and connections and the pipe installation and the valves and all that and the condensate and make sure that fits. So take that seriously. Get your permit stuff going early because one of these 3 might be backed up at any particular time. The one big difference between Seattle's rules and what the state adopted is that in Seattle you have to have your heat pump big enough to supply 100% of your hot water requirement at 40 degree outside temperature, and 50% at our design temperature of 24. With Washington State, any place outside of Seattle or another community that adopts Seattle rules, you only have to provide 50% of the maximum capacity that you're going to use with heat pump at 40 degrees. But keep in mind that our current systems for sizing heat pump or sizing any kind of hot water system, especially for residential, wildly overstates the capacity. So designing for 50% according to traditional plumbing rules might get you all of your capacity handled there. Hey, there's EcoSizer.
Yeah, Ecosizer. So there's a link up in the top left there. I'll talk about this. This was a program that was funded by California to help designers design. Right now, we're actually doing a redesign of the whole program. It's going to have much more capability, but there's a little email down there, info@Ecotope. And if there are things that you would like to see inside of Ecosizer, please send an email to there. We actually, the funder that we have funding this program and this development has to kind of see the demand, and that will sort of, be the motivation to fund it. So kind of works really straightforward. But this is a great program. I've designed about 90 systems, probably half of them using the program. I've never come up short on hot water in any design. So there is some safety kind of built in. But again, this is kind of the original where you'll end up. Its results will result in a 16-hour runtime, and so typically you have to kind of pay attention to that when you're sizing. But usually you can kind of vary between, so you can let the program get you pretty close to sizing, and then there's this little bar over to the right once you use it, and you can kind of you can dial in your heat pump capacity at your design condition, and then what follows is your storage. And so you've got a pretty precise way to kind of track those trade-offs.
And I've been playing with this. It's something that's very friendly to non-engineers. Got the axis on the left there, that vertical axis is the heating capacity of your heat pumps, and then along the bottom is your tank sizing volume, and you can just sort of slide things along there, and based on how much room you have and other factors, you can pick anything along that line. But you can see how dramatically more heat pump capacity you have to buy, which is very expensive if you have very small storage. And then you get down to where you have large storage and you've cut your heat pump size by 2/3 or something. That's cutting the cost, and it's cutting the electrical demand.
Yep.
Do you guys have time for a couple quick questions?
Sure.
All right. Relating back to heat pump systems located in like a parking garage, Phoebe was wondering if there's a certain level of fencing or other security that you might recommend for those systems.
Yeah, absolutely. We've typically, when we put all our equipment in a mechanical room in a garage, usually like cyclone fencing or graded fencing is a pretty good way to kind of enclose the plants. And obviously you have to have access to it. So a really sort of a good value play is to kind of put in just a big, like a cyclone fence, one that has kind of a sliding gate. Like I've seen that before. When you get into these large tank sizes, sometimes the standard doors don't work. And so we have been just opting for removing one whole wall and just replacing that with a chain link. You can also remove, 2 walls and kind of put your heat pumps in that room, kind of sitting next to that chain link. But the key is kind of making sure your heat pumps have access to a large volume of air, and that air is not being discharged into an enclosed room where you're pulling the same air in.
And just note that this is a match made in heaven for that type of system, because there's a requirement to be moving air through the garage anyway. So you have, if you coordinate this, then you have big fans already set up that are drawing air through the garage to keep the carbon monoxide levels down, and those can be your essentially moving all that chilled air back out of the building. It's amazing. I've been in garages, even I've measured it even like just 50 or 60 feet away from a big, like 30-foot wide open garage entrance, a little bit above, and they stay around 50 degrees, even in super cold weather. So that works out. I'm however, not I'm a much bigger fan of this, the CO2 based systems, because you have that greater flexibility with temperatures.
Thank you. And then the other one was, I think about a couple slides ago, they're wondering about secondary condensate pans and piping to lawn and garden.
Yeah, so condensate, Stephen Hart has approved on one of my projects us routing condensate to a dry sump outside of a building. What I typically, first step that I would do is I would, instead of calling it condensate, because I don't think that's what it is, I would call it defrost melt. And the defrost melt water is, it doesn't trigger reviewing code officials like condensate does. And so, that's one strategy, but the plumbing codes kind of say what we're allowed to do. And I would certainly reach out to the King County plumbing team, the David and Stephen. And if you've got any question about that, but I've gotten pretty good response from both of those folks at King County, and you just sort of ask where you can route this stuff. But it's really we're just draining the defrost melt water.
But you definitely don't want to just end up surprising them late in the game with no condensate drain into the sewer.
Right.
They would be very unhappy with you.
Yes, but if you've got a hardship, they're open to those, and there is some flexibility there.
Defrost melt, thank you.
Here's the next slide on Appendix M. So I'll jump in here. So this is, we haven't talked about it yet, but there's a new, within the UPC, there's an appendix in there that's been approved. It was approved in 2018 for Seattle. It's now approved for all of Washington State. Appendix M allows an alternative sizing approach, and so the alternative is using IAPMO's tool called WDC 2.0. If you haven't used it, it's a pretty nice little calculator. What you'll end up realizing is that your overall pipe sizing will go down 1 to 2 nominal sizes. That can have pretty big savings both on material and on meter costs, so connection fees are bigger with the larger size, and so there's some strategies there. But it's overall a very cost-effective approach. And this was 2050 partners down in California. We worked with AEA, Frontier, Skinner, UC Davis, but essentially looking at about 20 different metered water use buildings. And the different units are shown across the bottom on this graph. And what we ended up doing is actually observing the peak flow rate in these buildings, the 99th percentile, and that's plotted with that black dot. Then the blue would be the Appendix M theoretical design, And that red is the Appendix A, which is the traditional hot water sizing strategy. And you can see kind of where those peaks would lie. So this is the Hunter's curve stuff. And so we can see that the actual flow in these buildings is actually half or less of an Appendix M. Now there's a couple cases where it's kind of close. But I think the takeaway I think in this slide is really that we've still got room inside of Appendix M to do the sizing at that level. You're still safe. We've got one design now that's being built, so it's kind of a new strategy. So there's not a lot out there, but yeah, that's the data out there. The data suggests that the flows in these buildings are a lot lower than we think they are.
And that's where looking at a system that is in an existing building, and you're going to replace it, if it probably, since Appendix M is relatively new, in all likelihood your building was constructed according to Appendix A, which means that you might have 10 or 15 times the capacity that you actually need. So you don't have to replace it one for one. You should get a meter on there and find out, how long would you need to meter, by the way, Shawn, to really figure out peak flows? A month or what?
Yeah, I would say, you get a peak event at least twice a week. It's the morning time. Maybe it's depending on what the occupancy is. I'll tell you when your peak is, but morning or evening. But you usually want to have a couple weeks on there just to kind of flush it out. But the peak isn't really that important if you're doing a retrofit. You want to know the temperature maintenance, but you've got this really large piping system existing, and so you're going to replace it with a kind of a more efficient system, one that's sort of more right sized, and so you just got oversized piping. Oversized piping is higher heat loss, so you'll have to deal with that. The pipe's already there. But usually in a retrofit, the peak isn't so important. The peak is important, and there's enough data out there to suggest that 0.1 GPM per occupant is a pretty good sort of target to start at. This is not, a UPC certified official, but that's about what we've seen. If you look at the cumulative distribution plots of all these buildings, the 99th percentile is what's shown there, and that equates to about 0.1 GPM per occupant. And that is about what we see in hot water flows in buildings.
This is good to know, and especially if it means the difference between having to have City Light come out and upsize your transformer versus being able to get by with the power you already have in house. You might want to look at what your peak requirements are.
Absolutely.
All right, we're going to move into another segment here: distribution systems and temperature maintenance. Just one little code thing first. Note that if it's a single pass heat pump water heater, I think Shawn mentioned this a few minutes ago, that's got to be a separate system. I highlighted in red there that it's physically decoupled. If it's multi-pass, then that will work fine with bringing the lukewarm water back to the primary water state storage to get reheated. Now, we're back to that diagram again.
Yes, and so I think this is really trying to make the point on thermal stratification, and the reason that single pass is so nice, because what happens is you're actually delivering the hot water on top, and you're trying to push this plunger between the hot and the cold line down to the bottom, and then that water is sort of sitting on top ready to go. But thermal stratification is sort of the key in all of this stuff, and you have to really be thinking about having a stratified tank setup where you've got lots of available hot water sitting at the top, either parallel or series tank arrangement, but that you can handle the big draw that's going to happen, for the morning or evening rush. The pH diagram below, again, that's the cycle of the heat pump, kind of going around in its loop. And I'd be happy to explain how that works, but probably not in this session. Moving in, so this is sort of providing a little bit more picture behind the thermal stratification and how it impacts thermal system performance. And so if you look at the left, this is a single pass heat pump water heater, and it's got a dedicated temperature maintenance heat pump attached to it. And this sort of shows what's happening inside of that that dedicated tank there. So that's our separate dedicated system for temperature maintenance. The hot water circ is coming in and then kind of flushing that tank. That's that orange color, and that heat pump is taking that orange and turning it red, so making it usable hot water. 120 is sort of our usable temp range. And then the other tank is our primary hot water, and that is sort of mixing together. And so coming out of that secondary tank, the temperature maintenance tank, is your total design flow, and that would head towards your mixing valve. So the key there, some of the advantages to doing these separate, these dedicated systems are you get a little better equipment reliability. Having the dedicated plants on both sides, you get a little more storage volume having that additional in that temperature maintenance tank, and you can get higher heat pump water heater COPs, and then obviously the redundancies there. But this is typically set up for systems that are larger systems, or where you've got large temperature maintenance loads. The multi-pass heat pump, again, this is, as it says there, all eggs in one basket. This is traditionally how the gas boilers were set up. So we would bring our circ back into a primary tank, and the heat pump lets it rip. The issue there is that heat pumps are most efficient with the coldest entering water. So the colder the entering water, the more efficient the heat pump is. And when you are kind of mixing recirc in with that cold water, these systems will tend to be pushed to their limits, and so you'll get lower performance out of multi-pass. And so that's sort of indicated in some of the equipment out there that's set up as multi-pass. Those rating points aren't as high typically. But these can be challenging. If the heat pump's really sensitive to incoming cold, warm water coming into the heat pump, it can really stress your compressor. Sizing gets kind of tricky. You got to make sure that whatever your heat pump is can go to the minimum size to handle the temperature maintenance load, and then it's got to be able to ramp up to the max size to handle the hot water load. And so you have to be really careful. And this is why we've tend to decouple them, is because the loads are a lot smaller. And so if you've got a giant heat pump and it's constant volume trying to take care of a scenario on the side, it's not going to work. And that's what happened in that Pasadena project. It's too much on the heat pumps. They're not designed to handle that range, and the compressors can be impacted. So you have to be a little careful. That said, I've seen some multi-pass systems set up that are working pretty well. And so also kind of dependent on the brand as well. Yeah, and then both of these systems we kind of mentioned there, they require some controls, some smarts to kind of make sure things are operating as intended.
And so the take-home message then sounds like it might be that it might be tempting to go with a multi-pass arrangement because it's a little less complex and maybe involves some reduced equipment, but it's risky.
Yeah. I think if you've got the heat pump set up in a below grade parking garage, I've seen that work with multi-pass. So I don't want to completely shun it because there is some savings there. Most of the region has been kind of focused on the single pass. Not the region, but that's what a lot of the manufacturers are focused on. But there are a few out there that do have the multi-pass. And I don't think it's like, end of story in any way, but I think in terms of a value play, multi-pass is definitely a lot simpler system. And so if you can get one and you're confident that it's going to work, You know, it's certainly one. Yeah, I'm not dismissive of multi-pass, I guess is where I'm saying, but I like single. All right, so again, just reiterating the two options for temperature maintenance. We want to decouple those loads because they're smaller. They're usually offline. The water's coming back usually 110 or so. We want to bump it up to 120. And this is just kind of making the point, you can either do it as a swing tank on the right or as a parallel loop tank. And so on the right with the swing tank, again, we've got the circulation and the hot water supply out of your primary storage mixing together to sort of prime that temperature maintenance tank. And then out of that, we'll heads to your thermostatic mixing valve. But by keeping that hot water return away from the single pass machines, the single pass machines operate much more efficiently. The same side on the left is the parallel loop tank. Again, this is an application, you set it up this way when you've got large circ loads. So over 100 watts of an apartment for apartment projects, or really big loads, really big apartment projects, you know, 200 units, 250 or more. But we've done both on big and large project, big and small projects, sorry, big, yeah, large and small projects with success. So it's really just, you know, the Ecosizer should keep you mostly out of trouble on that front.
So are they equivalent in your mind, or do you tend to do one or the other of these, the swing tank or the loop tank?
Yeah, that's a good question. You know, the whole journey that we've been on has been kind of an experiment, and we kind of started at multi-pass, putting everything together, and that was a disaster. So it was like that didn't work, and then we started to evolve these. And most of the stuff that we're doing now has been the swing tank, just because it's less cost. You don't need that extra heat pump, and costs are pretty sensitive in this world in building. So that tends to be the system. You know, most of the projects tend to be less than, you know, 300. So I like that approach, just for, you don't have to buy that secondary heat pump. But sometimes the loads are so big that you'll want to drive the temperature maintenance. So not a very great answer, I realize, but I would just say that bigger temperature maintenance loads, bigger buildings should probably err towards the multi-pass heat pump, the parallel parallel heat pump temperature maintenance system. And the smaller stuff should be on more swing tank. But again, both of those have to be set up with single pass heat pumps. That's super important for both of these.
Got it. Okay. Oh, some sort of, I was supposed to be doing some little graphic things there for you. But anyway, now we're going to move on to sizing. I already had that slide, so we can just go past that. We do allow a certain amount of supplemental electric resistance heat in Seattle. Defrost, the temperature maintenance we just talked about, some heat trace, and backup for really cold temperatures. Obviously, that backup for cold temperatures isn't going to be necessary when you're using one of the CO2-based systems, because they're good to, what, 5 degrees. So you can reduce your electric load a great deal. Shawn.
Okay. I mentioned kind of the big hot water dump loads that happen in our projects. So this is a market rate example. It's 100 and it's about 200 units up in Yesler Terrace. And we can kind of see the variation you'll see in a typical week. And so Duane, you asked, you know, how long do you have to kind of meter something? And you'll notice there's usually a design day, and it tends to be like Monday morning, where you get this frantic rush, and then you'll get more of an average kind of day in that orange run. And so obviously as designers, we want to be capturing that design day. But most of the, you know, what we tend to do is we take a design day inside of Ecosizer, and we've got that sort of load shape in there. And one of the things that's happening inside of Ecosizer in the evolution is we're going to make it customizable so you can put any load shape in. But you do have to kind of pay attention that the peak hot water load is going to be the coldest day of the water day of the year, which is around April, because that's when the snow is melting, and so the groundwater is particularly cold right around there. So right around now, for April, May, that's your design water day. But then your design air day would be obviously your winter design load. So you have to kind of factor both of those into it. On the air side, you have to make sure your heat pump is, what it's producing on that design day. And then on the water side, you want to make sure you capture this demand load, because you can see there's a little bit of difference between the average and the peak.
Oh, we already did Ecosizer. We'll just keep going.
So I mentioned the heat. We talked about defrost, we talked about defrost meltwater, but we talked about heat pumps, and heat pumps will typically lose capacity as the temperature drops. And you can see over to the right, these are curves from, I'm not sure which manufacturer, but it kind of shows at about 40 stays steady, and then it starts to drop. And different manufacturers, different refrigerants have different profiles. So this is just one example, and you can kind of see that 40 degree, it's pretty small. We're at just under 140,000 BTUs per hour. And if we drop down to our design temp at 24, the orange line, we've lost, roughly 30% or so, down to 120 just for that increment. And so if you're trying to meet the load on that design day, then you would select your heat pumps and assume that they're 120, not 140. And that would be your design condition for your output. I would, one other thing I would say is that you have to keep in mind, back on the defrost, a heat pump will be rated for a particular output. So in this case, it's 120. But the thing you have to understand is that there's a defrost factor, C sub D, that what ends up happening is you're not actually running the full 1 hour at 120. You're probably running more like 50, 60% at 120. So your actual output, based on where you're at, it's actually going to be much lower in 1 hour, because the machine has to take a rest, melt the ice, and then you get you get your 120 or whatever its derated function is. But that's why these machines start to lose capacity. And so there's both just a thermodynamic limit, as well as you're not actually running for 1 hour at 120. So you won't actually get all of that. And you have to make sure that you've got your backup systems on, or secondary systems here, and hoping that they're not defrosting together. But you will notice that on design days, and you have to pay attention to that. And you won't get 120 if it's stopping to also defrost.
Is that dotted orange line that's like an 82?
Yeah.
So that's real world for sizing for a super cold day, incorporating defrost.
Correct. Yeah. And the defrost factors aren't well known by the manufacturers. Sometimes you can get it out of them, but I would recommend trying to push that to try to understand. There's 4 or 5 different ways to defrost. That's also another variable. Those come with the different technologies. Blowing just regular 40-degree garage air over frozen coils does not melt very fast. I will tell you that. So you need to have a little bit more active defrost, hot gas injection or resistance coils. But the game is to keep that heat pump running. And so doing that, you need to shed that ice as quick as you can.
Okay.
Okay. Do you want to take this, or me, Duane?
I can start. Just
okay.
Note that there are refrigerant types that have wildly varying levels of global warming potential, and the state laws about refrigerants actually don't apply to water heating systems for some reason. They're still just applied to space heating. So there's our 410A has been our fallback for a long time, or 134A that you see highlighted there. And those have global warming potentials in the thousands, whereas the CO2 is by definition got a global warming potential of exactly 1. And right around 50% of all refrigerants used end up in the atmosphere, usually due to something during the life of the equipment where it just loses the whole load of refrigerant. So it's a really huge deal. All right, Shawn, what did I miss there?
Oh, that was great. You got most of it. I would just say keep an eye on that. In that table, there's a low ambient air temp, and that kind of shows you about how low these systems will operate. That does not factor in the defrost, but that just says if you present, a 134A machine with 35-degree air, that's probably about the limit of it. But those equipment, I've seen those rated down to 15 or so. It's just the 134A stuff is a higher cycle. It's a higher temp cycle, and so that 35 is sort of your limit. But that kind of shows you, basically 134A. Probably you're going to be, I wouldn't recommend putting those outside in our climate unless you've got a really solid defrost strategy. And there are some manufacturers that do have good defrost strategies. The 410A stuff, this has traditionally been the space heating refrigerant. You can use it for domestic hot water. The issue there is it doesn't make super hot water. 120 is probably your best. It will operate down to -5, but you have to pay attention to the capacity. It drops pretty severely. And then Duane mentioned the CO2 744. Those machines can typically handle into the negatives, and they can make 190-degree water upwards of. So those are nice, piece of equipment for water heating, and CO2 being GWP1. There's no more climate legislation around CO2.
We have someone wondering about R32.
Yeah,
Sure, that's a great.
Go ahead.
Okay, I would say that we are in the midst of a transition. Duane did touch on that a bit, but 410A is going to be replaced by likely 2 products, R32 and R454A. And one is owned by Daikin, one's owned by Honeywell, and so they're going to own the refrigerant for probably everyone. And then the 134A is going to transition to 513A, and then so those are those are going to be 2 transitions that we know about. GWP is about half in both of those transformations, I guess.
And you could see that if you're working for a client that cares about the future, long term, like if you're working for a university or a school system or something, that there might be some future proofing involved in going with the CO2 or one of the organic refrigerants, because R32, yeah, 675 is way better than 2000, but you could imagine that in the foreseeable future there might be legislation to squeeze that more. So you want to be conservative, go as low on this chain as you can. Buffer zones.
Yes. So this is again reiterating the idea that having heat pumps with access to big, with large open air is pretty important. I mentioned kind of an alternative way of setting up a mechanical room. If you look to the left, this is a plan view of a mechanical space. And the way this one was designed is there's a louvered entry, and then the machines are ducted out of that kind of closet into the main garage. There's another way to do it in the diagram to the upper right, and you could actually have a garage exhaust shaft, and you're just dumping your discharge air from your heat pumps into that garage exhaust. In some cases, that can replace your continuous ventilation requirement for parking garages. And I've done that and gotten it passed. So that's certainly kind of a nice dual use. But the key is that the heat pumps here need to have access to the big open airs. If you put them inside of a room and plan a room around it, then you've got to do a lot of messing around. But if you design a room that just has your water and your tanks and your piping, and then put your heat pumps on the outside and put a hole through it, then it's a lot less messing around. And so usually you can kind of tuck those into some of the corners. You can see one up in that diagram to the left. And some of the heat pumps have ducted ability, some don't. And so you kind of have to figure out what your configuration will work. And most of the reps can kind of help you out getting stuff dialed in.
And we could just mention this, we've already talked about Appendix M, but what I like about this slide is in the chart at the bottom, you can see the difference between the pipe size that was required for Appendix A versus for Appendix M. That's also a really big cost saving for the city's connection charge between a 4-inch pipe and a 2-inch pipe to a building.
Absolutely.
Just wanted to mention, in case anybody's looking at that water heating equipment efficiency table, there's this weird formula. Don't worry about it. I think it just says that it's got to meet federal standards, which is what they have to manufacture anyway. I wanted to mention one little thing that along with the 1/2 and 5/8, we've added 3/8 inch piping to our little exceptions in this table that says that for public labs, you can have 8 feet of pipe, because that's just going to make your piping configuration dramatically easier. And if you want a whole rant about that, let's get frosty beverages and talk about it. Just note that the fixture standards for Washington State, as of a few years ago, are 1.8 gallon a minute. That's better than WaterSense level fixtures, and that's for shower heads and lab faucets. So we already gone through Appendix M enough, but note that it does, in our current version, it allows the one pipe larger, but I think the study that Shawn showed you indicates that you don't need that one pipe size larger. The pipe insulation is different for what I'm calling direct versus the circulation loop. And this was confusing the way I had it in the 2018 code, so I've made it more clear what it all applies to. But the whole circulation loop gets an inch thicker insulation than just a straight shot from the water heating source to a fixture. The pipe insulation is required, that circulating system with the 1 inch thicker is required all the way around the loop. So supply and return back to the heater. I made this table because it's been so difficult for everybody, me included, to figure out what was actually required. You had to flip from C404 back to a table in C403 and then be lucky enough to find a footnote buried below that. So this puts all those thickness requirements in one table. Note that there's a different requirement for refrigerant piping. So if you're just doing refrigerant piping to connect a split system or something, be real clear about complying with those separate rules. For tank insulation, for big storage tanks, or little storage tanks, if you are going to store water at temps above 130, which might make sense because you're going to be mixing it anyway. If you could have smaller tanks if you store at 150, say, you just have to add an additional insulation for every 10 degrees above 130 that you go. And I think they come in 4-inch wraps that are meant for these kind of tanks. Another little thing is just, I think we mentioned before, you got to have a thermostatic balancing valve and a variable speed pump if you're doing a multiple riser system, which would be common in any large building. Temperature maintenance losses.
Yeah, so the takeaway here, this is a sampling. This is trying to kind of show both a seasonal effect and kind of showing a sampling of different apartments that we've measured. So the recirculation loop losses, the hard part about designing, say, a new building is this calculation. There are calculators out there. The ASPE has a calculator to calculate it. But you have to remember that the UA, I mean, the losses inside of our temperature maintenance loops are really just the UA, which is the pipe, heat loss characteristics. So the U value around that times the area, the surface area of that pipe, times the delta T between the fluid and the space you're routing through. And so if you can imagine, there's seasonal effects. And so you'll have the highest losses in, sort of the middle of the winter months, where it's coldest out. So if you've got, piping in a parking garage, that'll influence and increase your load. So you do have to be a little bit careful, especially if you're going into an existing building where you can measure the temperature maintenance loss, usually with a BTU meter, you can measure that. So we actually got some funding to go measure a bunch of existing buildings out, kind of in the region, and you can kind of see the histogram to the right. This is another local kind of data point, but these are 4 or 5 different temperature maintenance losses, and the way that we have been sort of characterizing these are on a watt per apartment basis. And this is just a way to normalize it so you can see it across different size buildings. But if you look at a 4-story, another 4-story, there's electric tank in the unit. So if you put an electric resistance tank in the unit, it was calculated to have a loss of about 60 watts an apartment. So electric tank inside of an apartment will always lose about 60 watts. So that's kind of your standard to measure against. 6/1, there's 3 6/1 buildings. You can see the variation there. The difference was mostly the piping being in the parking garage versus the heated space. But when it's in the parking garage, it has a bigger delta T across that insulation wall, and so you'd expect a higher number. One thing I would say is that if you can target 50 watts or less, what ends up happening is you don't ever trigger the swing tank backup resistance element when you're below that, right around 50, 55 actually. You won't actually trigger it. And that can have a huge impact when we get into load shift, because you can essentially turn off your temperature maintenance elements and completely shift, any power draw to the kind of the non-peak hours.
So Shawn, now we've got, for a new building, we've got much smaller pipes, much fatter insulation, the valves at each riser. Haven't we done stuff that's going to already cut these losses in half?
Yeah, I think we have. If we've got a spec in a building that's essentially representative of this round of, this new code, it should be significant. We saw 65, 70-ish kind of as an average. If you kind of look at this for a bigger building, and that would probably go down by 30, 40%. And so there's things you can do to kind of continue to push it. But yeah, I think if you're doing a pretty good job, following the code, good insulation values, getting below 50 should not be a problem.
And by the way, our county plumbing inspectors are about to launch a new program where they will be out inspecting insulation. Just remember, if you're doing the thermostatic mixing valve, that it's set so that it either reverts completely closed or maintains its position if you lose power for a while or lose circulation. Right. We're gonna, I think we need to move more quickly, but go ahead if you have something you want to say.
Yeah, I would say that this is a kind of a sample showing one particular brand of a thermostatic mixing valve. And the kind of the keys here are this becomes pretty critical for sizing. You want to make sure you're sizing your valves per the manufacturer. They kind of want them pretty fast going through those valves, so make sure you size those right. Just remember the 0.1 GPM per occupant, and when you're sizing a mixing valve, you have to add that primary flow plus your circ flow to get your total. One thing you have to be really careful of is your circ flow has to be at least the minimum flow that the valve is rated to perform at. Because in the middle of the night, that'll be one of the that'll be the primary flow element inside of that mixing valve will be the circulation, maintaining the temperature maintenance system. And you have to make sure that it's sized so that it can handle that min flow. It's usually a function of where your pump is set at.
Okay, demand response. We just have to have capability built in and this is just for small storage water heaters that we got to have capability built in to do demand response at some time in the future. Wanted to say that there are C406 credits that are required. Don't get alarmed by this number of credits. They kind of changed things so that they divided each of the old credits into about 6 for these things. It's a little more rational system that they've set up. But for hot water credits, like you look back up there at Group E, you need 53 credits there. Or no, let's see, Group R2, you'd need 45. Just with this, if you did shower drain heat recovery in your building, and another one that I've circled in red, the high performance temperature maintenance and some low flow shower heads, you're already there. Appendix M is good for 10 credits, even though, and that's just if you use the Appendix M size instead of taking advantage of the option to go one size larger. The commissioning is also getting taken more seriously at the building department here, so please note that you got to have the commissioning done, and someone is going to be out there actually making sure that it's done and the reports are submitted and the unresolved issues that come up in commissioning are resolved. This diagram is only to show that you're replacing, in this new code, when you're replacing water heating, if you're one of those types on the left, affordable housing or a hospital or something, you can be exempt for this cycle, but you got to do this future decarbonization plan. Any other kind of building, look in the middle there, you can see you'd be allowed to keep half of your current gas heat capacity and submit that plan. And if it's an emergency and you have to replace everything, you'd need to give us a bond that ensures that within 4 years you will replace 50% with that with heat pumps, so that the option to just do nothing and keep burning gas forever has gone away. And that decarbonization plan is a complete schematic design that shows everything that has to go on in there that's going to cost money, and shows all the equipment laid out, where it will go, all the architectural and structural changes you have to make, the electrical upgrades, that whole thing, and a schematic level cost estimate. So that is essential. It's going to be that it costs about 1% as much as actually doing the work, but it'll be that first step towards actually moving to heat pumps, which you'll have to do eventually. With alarms, just make sure that those are set up as required there to get those bullet pointed bits of information out, and then be clear about who gets this, where it comes, and how you're going to ensure that that's not just going to a web page that nobody even notices. Got to get it to cycle all the way around to somebody fixing something that goes wrong. Metering is required. Each dwelling unit has to get its own meter, and note that the plumbing inspectors are inspecting for these things now, and there's been a lot of heartache because I guess in years past they didn't. So make sure that every one of your apartment units has its own hot water meter. Some common challenges, Shawn.
Sure. Common challenges with air source, obviously managing the air is kind of crucial, and you have to kind of plan for it ahead of time like anything. But I think that managing that air is sort of the primary piece. Obviously, there's other pieces, but if you're inside of a parking garage, just making sure you've got adequate flow is super key for the kind of the air source machines. And then obviously not making them too far away, getting the heat pumps somewhat close. I've seen folks in California doing rooftop to, heat pumps to tanks in the basement. So yeah, but I would say that the air is sort of the key piece.
Or just use CO2 based systems, and you can put them anywhere and not worry about it.
Correct. Yeah.
Physical space.
Yeah, so we talked about the size being, maybe 1.5 times of a boiler plant, plus the, locations outside of that room for the actual air moving heat pumps. But they do take a little bit more planning up front. If you're working on new construction, SD phase is the time to really do your eco-sizer run and get things sort of situated. Then go talk to your equipment reps, and they'll help you kind of get things dialed in.
Excellent. Wanted to mention a few things about existing buildings before we close. Pretty much things that went in to start with can stay that way forever. But new stuff has to meet current code, and when we're doing a substantial alteration or a change of occupancy, or you're putting heat into an unconditioned building, that we consider almost a new building. We saw that. Just wanted to mention to you that this verbiage for the proposed code is here on slides. You can look at it at your leisure later, but it's saying, yeah, you gotta replace your hot water system with heat pump. If it's a really expensive electrical upgrade, that's one of the exemptions you get, and that would be defined as needing to get a new vault or an enlarged vault, or needing to trench across vehicle lanes on a street, or there's also a cost basis there. There's exempt systems, so little water heaters are exempt, and for buildings, they are affordable housing, institutional, nonprofits, or small buildings smaller than 20,000 square feet for now. There's that rule I mentioned that you could hold on to 50% of your existing gas water heating capacity, knowing that you probably don't need it, or you can have, if you really have to replace equipment right now, you can do it, but you have to post a bond that says you'll change the 50% out within 4 years. So just note that it's not just our code. We also have Seattle's getting close to finalizing the building emissions performance standards, which sets out a timetable over the next couple decades to change away from fossil fuel. And so you can decide to postpone the replacement with heat pumps, because of constraints on the cost right now, but just know that might cause you to have to replace your equipment later under the building energy emissions performance standards before that equipment is at the end of its useful life. So we got there. Thank you all so much. And I think we have just another word or two from our sponsor here.
Sure, you want me to do this before Q&A?
Sure.
Okay. Let me turn my camera on so you guys, it's not just a disembodied voice. Hello again. So we've got 2 more of these codes series alterations coming up just in a week. Oh my gosh, it's almost June. And then lighting, electric, and solar. And if you know Shawn from the Lighting Design Lab, he is going to be guest on that last one. And somebody asked in the chat, and right here it says the slide deck that Duane made and the recording of this will be available on our website, lightingdesignlab.com. There's Duane's, Shawn's, and I'm not Armando. Email Armando and ask him questions. Or email us in general at the Lighting Design Lab at seattle.gov.
So with that, now those of you who have questions and want to stay on the line, please fire away.
Yep, and we've got several. So let's start with over the course of the webinar, you've mentioned several reasons, but Cameron wants to know why, Duane, you recommend CO2 for the refrigerant for heat pump water heaters.
A couple things. One is that we looked at costs a while ago, the additional costs to do heat pump water heating versus a central gas system. And we kept getting this argument. Some people were adamantly saying it costs an extra $1,800 per apartment unit, and other people were saying, no, we know for sure it costs an extra $800. And it turns out that, in fact, the CO2 systems were the less expensive one. So you're not only getting a global warming potential of 1, but it was costing less per unit than putting one of the big reverse cycle chiller units in the basement. That and the fact that it operates at any temperature that we're likely to ever see in this region and works fine means that you don't have to worry about falling off performance standards at the colder temperatures that we occasionally get. And you can put these outside. I've walked by an installation on Capitol Hill that I think it's a 50-unit apartment, and it has maybe 4 of these those little suitcase-sized units out there, and they were whisper quiet. I mean, I could not hear them, and but they could sit on the roof or in the garden or someplace else that doesn't have to take up interior space like the reverse cycle chiller units do. So if that's not good enough, you can talk to me more.
Great. And then Phoebe was wondering, she just noticed that it's not uncommon to find storage tank nameplates that seem to have been modified informally or even effaced. And she was just wondering if you have any idea why that might be, or if you observe, if one observes that, what would a reasonable follow-up be to that?
Shawn, you want to take that?
I don't know if I have an answer for that. I don't know if I've seen that, but yeah, I don't have a lot for that one.
I can't imagine why. And I know that the boiler inspectors do want to come around and check these on a regular basis to make sure they're still everything's still shipshape. So I'm not sure why anyone would do that, or if it's actually that common.
Yeah.
Okay. Phoebe, I hope you caught that. And oh, Cameron wondered if either of you had a source on data regarding heat pump water heaters in conditioned spaces. I pointed Cameron to PNNL and NIA, but if you guys have, you know, less reporty type data, that you recommend for Cameron?
I mean, there's a lot of work going on with, especially in retrofitting apartments that have electric resistance tanks inside of the units. Retrofitting those systems with heat pump water heaters, that can be an expensive route to go compared to central, but sometimes that's what you've got to work with. But there are, I mean, NEA, BPA, and then PG&E, they've got quite a few training programs out there that talk about this. I mean, if someone wanted to email me specifically, Shawn at Ecotope, I could probably find a couple reports on that. But we've done some experiments with developing smart closets inside of apartments.
I am really opposed to the idea of putting a heat pump water heater inside an apartment. Just because you don't have typically the space, the noise can be a problem, and the unintentional cooling of the space can be irritating to people. So I think that's a lousy way to go. On the other hand, putting a heat pump water heater in a commercial kitchen is great, because it's always too hot in there. The cooler air that comes out of that little water heater would probably be welcome in the kitchen. So you could do all right.
Some moisture mitigation there too. And then, Alexander wanted to make a point that parking garages are pretty dirty. The air is pretty dirty. So how do you keep coils clean there?
Yeah, no, I would agree with that. They are dirty. Obviously putting a filter on those coils, pretty important, but they have to be cleaned. And a lot of the equipment can simply be just hosed off. And so having a hose nearby and a drain could certainly work. Some of them are more delicate and they can't be sprayed. So they have to have kind of traditional, coil brushes. But in any case, outside is also fairly dirty too. And so, urban environments, but, my key takeaway is that, you've got to clean those coils at least twice a year because they build up regardless of where they're at. But when a new construction project is just completed and you've got all the concrete dust kind of still in the garages, and that's where you see a really big. So when you're first starting up, you want to make sure you've protected those coils and you clean them after, before handoff, because they will be filthy.
So many things to have in your checklist of.
Yeah.
Is that part of commissioning too? Do you know?
Commissioning is typically making sure that the systems are installed per spec, and typically the commissioning on closeout will ask to clean out as a closeout piece to clean off the coils for delivery. So that typically is part of that.
Should be right. Cameron has another request for data or a reference source. Duane, you said that you had that chart about refrigerant lost for systems over there, or you mentioned that when we were showing the not the COP, the greenhouse gas. Yeah, and Cameron works at the port and they have to report GHG sources, and so he's wondering if you had a reference for that talked about the losses.
I have to go back and find it myself online, so probably wouldn't be any faster at it than Cameron would be.
You just have it online. Cameron, find Google. Okay, Ryan wanted to know if there was an acceptable range for resistance backup per heat pump water heater. For example, if the heat pump water heater output is 51 kilowatts at 40 degrees Fahrenheit, but readily available EWH are rated for 54 kilowatts.
So yes, I mean, that comes into your reliability redundancy kind of strategy for design. There's a couple ways to do it. If you have a single heat pump, having a, N+1 will give you kind of 2 stages of reliability. So if one goes down, when you've got a backup resistance, so backup resistance would be kind of a value play on buying that extra heat pump. So the resistance boiler are a lot less cost. And you essentially do want to, if you've only got 2, then you sort of want to pay, you want to put in the full capacity that you're getting at your design condition for your heat pump. You want to put that in as resistance capacity as a backup. So when you're using like the Senko 2 product, if you've got 5-6 modules of heat pump, then you could argue you probably have enough redundancy there that you don't need the backup resistance on that. But there might be other reasons why you'd want it. But typically, our strategy has been N+1. So if the design calls for 5 Senko 2, equivalent of 5 Senko 2s, you put 6 in. And that's a pretty easy upgrade there. And then and then depending on the load on the building, if you can do it all with a single larger heat pump water heater, then having a backup in resistance is probably a pretty good value play too. And then obviously more heat pumps and more stages, are going to be just that much more reliable.
And then he was asking more in respect to being code compliant, Duane. Is there, yeah. But thank you, Shawn.
Yes.
So code compliant, can you try that again then? Code compliant in what way?
The range for resistance backup per heat pump water heater.
And I'm confused about what part of this is code requirement.
It might have been the backup systems slide that talked about that you can back it up with gas or electric. And I think maybe the question is focused on, is there a limit to that backup within this?
And those are pretty clearly spelled out in the code language in section C404 that that you're permitted to have backup, but it's constrained, I think, as a percentage of the size of the heat pump water heater. We just want to make sure that these don't just turn to toaster ovens when it gets cold out.
Okay, and then Jeremy's asking, is there an exemption for retro if there are large cost impacts due to structural upgrades based on weight increases for the large storage tank increases? That question first.
No, there is not. And that said, it's recognized that this is going to be expensive and messy and disruptive for everybody. Not just the water heating, but also for space heating as we switch out from gas systems, which are cheap and compact and quiet and easy to deal with. Once again, the options for moving something outside might be explored, but no, if we know that it's going to be expensive. We've also committed as a city and a state to moving off of fossil fuels, and so we're going to start doing it. That, once again, that's why I would suggest that your actual need is probably dramatically smaller than your current capacity, and you should not assume that you have to replace that whole capacity in your building. You're probably going to replace, Shawn, 10 or 20% of it?
Yeah, kind of depends on your storage, but yeah, 10, 20, 50, but yeah.
And then this next part of his question, kind of riffs off that. Please explain capacity if we're going from BTU storage system to newer, high efficient, larger BTU, but no storage. Does that mean we still can't go on a higher BTU option boiler?
Right. We're not giving any kind of particular credit for just higher efficiency use of fossil fuel.
Yeah, that's what I was asking.
Okay, and that is one more. What are the details of code requirements for insulating hot water piping between the heat pumps and the mechanical room on the roof? Cladding, insulation between anchors and pipe, etc.
I would prefer more.
So we're talking about between the heat pump and the storage tank. I think that's the standard pipe insulation, because it's the circulating loop that needs the extra 1 inch.
Because
Okay,
I as a business-
that's all the questions that we have right now. Do you want to give a couple seconds to see if anything else comes in? Oh, one just did come in. It's 11:50. We've got time probably. Emily says, practically in an existing building that has exceeded its kilowatt budget per C404.2.1, exception 1, but is adding a single kitchenette, are we now required to add a heat pump for that kitchenette?
In general, no. I think we've got exceptions that allow a specific small individual heat pump, not heat pump, individual little water heaters that serve only a single fixture or a limited cluster of fixtures. And we've got that clarified in this next code. So if something like that does come up, please give us a call and tell us the situation, and we'll see what options are available for you.
Okay, and one more just came in. This was actually, he asked it earlier, but I needed clarification. And so Eric was wondering, Shawn, do you suggest plugging in the design day air and water for sizing, or is that overly conservative? And his clarification was, you had mentioned those 2 types of design days, but how would you recommend designing them with both of those types of days in mind?
Yeah, that's a great question. I would say that heat pump selections should be designed for your air day. So wherever you're located, if you're in a parking garage, 40 degree, if you're outside, 24, 19, whatever number you're using, but 24 is kind of our ASHRAE standard. And I think that's going to be your bigger driver, because the variation in the water temp between that cold day, which would be call it January or February, the water temp will be pretty close to the peak cold. It might be a couple degrees warmer as you're kind of peeling out, but we've measured the city water coming into about 8 or 10 buildings, so we've got a curve on it, but peaks in end of September, coldest in April, and kind of linear outside of that. So I would say in terms of the design scenario, I would say sizing for your air side is going to be probably more relevant, because you're not going to see a huge difference in the water. But 50 degree, 47, 48, you can enter that into EcoSizer, but I've never gotten into trouble on that entering 50 degree. So I think you're fine at 50 and focus more on the air side.
Great. That is all we have.
Take the online survey that you'll get pinged with when you exit. Everybody, thanks for being on the call. And we're easy to find. Please contact us if you got further questions.
Yep. Thank you to you both, and we will see you next week.
Bye.